Hello there, and welcome to Sleepy Science. Tonight we are not looking outward at stars or oceans or distant horizons. Tonight we are turning inward, into the quiet, invisible world that lives inside you right now. A world smaller than anything the human eye can see, yet more complex than any city ever built. Tonight, we are going to explore allergies, that familiar tickle in the throat, the way your eyes water in spring, the sneeze that comes out of nowhere on a walk through a park. These small, ordinary things are the surface of something enormous. Beneath every sneeze is a story of evolution, of microscopic armies, of ancient signals still humming through your blood right now as you lie here. The immune system never sleeps. Even as you do, it is at work, sorting, signaling, defending, and sometimes misunderstanding. If these quiet journeys into science bring you a little peace at the end of the day, I would love for you to like and subscribe, or leave a gentle thought in the comments below. It helps other tired people find their way here. But for now, all you need to do is breathe. Settle in. Let the world outside grow a little quieter, and let the soft science of your own body carry you toward rest. Let us begin. Your immune system contains more individual cells than there are stars visible in the night sky with the naked eye. Right now, moving through your bloodstream, patrolling the lining of your lungs and gut and skin, there are trillions of immune cells, white blood cells of dozens of different types. Each one has a specific job. Each one communicates with others through chemical signals so precise they make our most advanced computer languages look clumsy. Some of these cells are scouts, roaming tissues looking for anything unfamiliar. Some are killers, designed to destroy specific targets with remarkable accuracy. Some are memory keepers, holding a perfect molecular record of every threat the body has encountered, sometimes for an entire lifetime. This whole living city, this whole invisible civilization inside you, operates without any conscious input from you at all. You do not think about it. You do not direct it. It simply runs, quietly and tirelessly, every second of your life. An allergy is what happens when this extraordinary system makes a very specific kind of mistake. It looks at something entirely harmless, a pollen grain, a dust mite, a fragment of peanut protein, and it decides with complete conviction that this thing is dangerous, not mildly suspicious, not worth a second look, genuinely, urgently dangerous. And so it responds the way it responds to real threats, with everything it has: the sneezing, the itching, the runny nose, the watery eyes. These are not malfunctions. They are a perfectly functioning system aimed at the wrong target, like a fire alarm going off in a building that is not on fire. The alarm itself is working exactly as it should. It is simply responding to the wrong signal. There is something almost tender about that when you sit with it, your body trying so hard to take care of you that it fights battles that do not need to be fought, loyal to a fault. The part of the immune system most involved in allergic reactions is called immunoglobulin E, or IgE. It is a type of antibody, a tiny Y-shaped protein produced by immune cells called B cells. Most antibodies in the body fall into other categories: immunoglobulin G, immunoglobulin A, immunoglobulin M. These are the workhorses of the immune system, the ones that fight viruses and bacteria and patrol your blood in large numbers. IgE is different. It exists in incredibly small quantities in the blood of most people. In someone without allergies, IgE is barely detectable. It makes up less than 1/1000% of all the antibodies in the body. It is the rarest of the antibodies. And yet, it is the one responsible for all classic allergic reactions. IgE evolved, scientists believe, primarily to defend the body against parasites. Specifically against parasitic worms, a class of organisms called helminths that have plagued humans and our ancestors for millions of years. These worms are large by immune system standards. They cannot be engulfed and destroyed the way a bacterium can. They require a different kind of response. IgE, working alongside certain immune cells, triggers the inflammatory responses, the mucus production, the muscle contractions, the tissue responses that help the body expel or wall off parasitic invaders. The sneezing and the runny nose and the itching that make allergies so miserable are, at their root, the body trying to wash something out, to expel an invader, to create an environment so inhospitable that a worm or a parasite cannot stay. The problem is that in the modern world, especially in wealthy, industrialized countries, parasitic worm infections are rare. The immune system still has all of its ancient hardware, all of its IgE, all of its mast cells and basophils and eosinophils, all of its inflammation machinery. But it has very few genuine parasites to use it on. And so, for reasons scientists are still working to fully understand, it sometimes turns that machinery on harmless things instead. Pollen, which drifts through the air the way parasite eggs once did. Food proteins, which pass through the gut the way worms once did. Pet dander, which coats surfaces the way parasitic material once did. The ancient system is still running. It simply does not have the enemy it was built for. Mast cells are among the most important players in an allergic reaction, and they live almost entirely in your tissues rather than your blood. They sit just beneath the surface of the skin, lining the airways, living in the gut, clustering near blood vessels. They are there, quietly waiting, loaded with chemical grenades called granules. These granules contain histamine and dozens of other signaling molecules. Under normal circumstances, mast cells sit peacefully. They have receptors on their surfaces designed to bind to IgE antibodies. When a person becomes sensitized to an allergen, which means when their immune system has decided something is a threat and made IgE antibodies against it, those IgE antibodies attach themselves to mast cells. The mast cells are now armed. They are holding a set of very specific keys, each one shaped to match one particular allergen. The next time that allergen appears, it crosses the threshold like the wrong person entering a room full of guards who have been given a description. The allergen binds to the IgE antibodies on the mast cell surface. Two IgE molecules bridge together, a signal fires, and in an instant, the mast cell ruptures its granules. It releases histamine and dozens of other molecules in a burst that takes only seconds. Histamine, in particular, is responsible for most of the familiar allergy symptoms. It causes blood vessels to dilate and become leaky, which creates redness and swelling. It stimulates nerve endings, causing the characteristic itching. It triggers mucus production in the nose and airways. It makes smooth muscle in the airways contract, which in severe cases can make breathing difficult. All of this from one mast cell in seconds. And it does not happen in just one cell. When a sensitized person is exposed to an allergen, thousands of mast cells in the affected tissues fire simultaneously. It is less like a single alarm going off and more like an entire city's alarm system activating at once. The response is immediate, powerful, and impossible to ignore. The process of becoming allergic to something is called sensitization, and it usually happens without any symptoms at all. This surprises many people. The first time the immune system encounters a substance it will eventually become allergic to, nothing dramatic happens. You do not sneeze. You do not itch. You feel nothing. The immune system simply notices the substance, processes it, and, for reasons scientists are still investigating, decides to make eager antibodies against it. This is called the sensitization phase. The immune system is loading the gun without firing it. It is only on subsequent exposures, once the mast cells are armed with IgE and the memory cells are primed and ready, that the reaction occurs. This explains why people sometimes say they have eaten a food for years without any problem and then one day, suddenly, have a reaction to it. They were not reacting the first time or the second time or the 100th time because sensitization was quietly building in the background. The reaction on day 101 is not random. It is the system finally crossing a threshold it has been approaching for a long time. What determines whether the immune system decides something is dangerous and worth making IgE against is one of the most fascinating and still partially unsolved questions in all of immunology. Genetics plays a role. A tendency toward allergies runs in families. If both of your parents have allergic diseases, your own likelihood of developing them is significantly higher than if neither parent does. But genetics is not destiny. Identical twins who share the same DNA do not always share the same allergies. The environment matters enormously. The timing of exposures matters. The state of the immune system at the moment of first contact matters. Whether or not a person has been exposed to certain infections or parasites early in life matters. It is a conversation between genes and world, and allergies are one of the possible outcomes of that conversation. One of the most elegant and thought-provoking ideas in allergy research is called the hygiene hypothesis. It was first proposed in 1989 by a British epidemiologist named David Strachan, who noticed something interesting in the data. Children who grew up in larger families, with more siblings, had lower rates of hay fever than children who grew up in smaller families. Children raised on farms had fewer allergies than children raised in cities. Children in less industrialized countries had fewer allergic diseases overall than children in wealthy, sanitized environments. His explanation was careful and specific. He did not say that being dirty was protective. He said that early life exposure to a wide variety of microorganisms, the bacteria and viruses and parasites that previous generations encountered routinely seemed to train the immune system in ways that made it less likely to overreact to harmless things. Without those early encounters, the immune system might be missing important input, important calibration. Left to its own devices, without sufficient microbial conversation in early childhood, it might remain in a kind of alert, reactive state, primed to respond to things that do not deserve a response. The hygiene hypothesis has been refined considerably since Strachan first proposed it. Many scientists now prefer the term old friends hypothesis, coined by the immunologist Graham Rook, which better captures the idea. It is not about hygiene in the sense of cleanliness at all. It is about the specific organisms that mammals evolved alongside over millions of years. The gut bacteria, the soil bacteria, the parasitic worms. These ancient companions shaped the immune system over deep evolutionary time. They are not random contaminants. They are, in a sense, teachers. When modern life removes them from the picture, particularly in the critical early years of immune development, the immune system may lose access to lessons it needs. This is still an active and sometimes debated area of research. The full picture is almost certainly more complicated than any single hypothesis can capture. But it has changed the way scientists think about the rise of allergic disease in the modern world, and it hints at something profound, that health is not just about absence of pathogens. It is about the right kinds of relationships between the body and the microbial world it evolved with. The lining of your gut is one of the most immunologically active surfaces in the entire body. If you could unfold and spread out all of the surface area of the small intestine alone, it would cover an area roughly the size of a tennis court. And across that enormous surface, there are more immune cells than anywhere else in the body. This makes sense when you think about it. The gut is the place where things from the outside world, food, drink, microorganisms, come into direct contact with the inside of the body. The immune system there faces a challenge unique in the body. It must decide, constantly and rapidly, what to tolerate and what to attack. Food proteins should be tolerated. Dangerous bacteria should be attacked. The gut-associated immune tissue navigates this distinction millions of times a day for an entire lifetime. When this decision-making process goes wrong, food allergies are one of the possible results. The immune system decides that a particular food protein is an enemy rather than a nutrient. It builds IgE against it. And from that point forward, every encounter with that food triggers an immune response. The 8 foods responsible for the vast majority of food allergies, peanuts, tree nuts, milk, eggs, wheat, soy, fish, and shellfish, are not special in any chemical sense that makes them obviously different from other foods. What makes them common allergens is likely a combination of how their proteins survive digestion, how frequently they are encountered, and certain properties that make them more likely to be picked up and processed by the immune system in a particular way. Food allergy in infants and young children is far more common than food allergy in adults. Most children with milk or egg allergies outgrow them by school age. The immune system, as it matures and as the gut develops a more robust and settled relationship with the microbial world, seems to learn to tolerate things it once reacted against. Peanut allergy, however, tends to be more persistent. Less than 20% of children with peanut allergy outgrow it, which is why it receives so much clinical attention and why it has driven so much research into whether early introduction of peanut proteins can prevent sensitization from occurring in the first place. The LEAP trial, which stands for Learning Early About Peanut Allergy, was one of the most significant allergy studies of the 21st century. It published its results in 2015, and those results surprised almost everyone. For decades, the standard advice given to parents was that children, especially children at high risk for allergies, should avoid common allergens like peanuts in early life. Keep them away from the thing, the logic went, and the immune system would not have a chance to become sensitized to it. This seemed intuitively reasonable, but the data did not support it. The LEAP trial took over 600 infants who were already showing signs of eczema or egg allergy, both indicators of elevated allergy risk, and divided them randomly into two groups. One group would consume peanut products regularly, starting in early infancy. The other would avoid peanuts entirely, following the traditional advice. They followed these children until age 5, and then measured rates of peanut allergy. The results were striking. In the group that had been regularly consuming peanut products since infancy, only about 3% developed peanut allergy by age 5. In the avoidance group, over 17% had developed peanut allergy. Regular early consumption of peanuts reduced the rate of allergy development by more than 80%. The conclusion was almost the reverse of what had been believed for decades. Exposing the immune system to a food early, when the gut and immune system are still developing and learning, appears to teach it to tolerate that food, rather than react against it. Avoidance, paradoxically, may increase risk. This finding prompted major changes in clinical guidelines around the world. Pediatric allergy organizations in the United States, the United Kingdom, and Australia now recommend early introduction of peanut-containing foods for most infants, including those at elevated risk. It is one of the clearest examples of science not just confirming what was assumed, but turning a long-held belief completely on its head, with significant consequences for real people, for children who might never need to carry an epinephrine auto-injector if they had peanuts introduced early enough. The skin is the body's first barrier. It covers the entire outer surface, roughly 2 square meters in an adult, and it does an extraordinary job of keeping the outside world out. But the skin is also, in people with certain types of allergies, a site of failure and a site of entry. One of the most interesting theories in modern allergy research suggests that many food allergies may actually begin at the skin, not in the gut at all. This is called the dual allergen exposure hypothesis. It proposes that there are 2 ways the immune system can encounter a food protein. Through the gut, where the environment favors tolerance, where the right microbial signals and the right immune cell populations tend to lead the immune system toward peaceful coexistence with food molecules. And through the skin, particularly through damaged or inflamed skin, where the environment is different, where the signals sent to the immune system are more likely to trigger an alert, reactive response rather than a tolerant one. Eczema, the chronic inflammatory skin condition that makes skin dry, itchy, and vulnerable, is strongly associated with the development of food allergies. Children with eczema are far more likely to develop peanut allergy, for example, than children without it. And one plausible explanation is that in eczema-affected skin, tiny traces of food proteins can penetrate through the damaged skin barrier, encounter the immune system in this altered, primed environment, and trigger sensitization before the gut has had a chance to establish tolerance. It is a somewhat unsettling idea that the route of first contact with an allergen may help determine whether you become tolerant or reactive, that a small patch of dry, inflamed skin on an infant's cheek might be the beginning of a lifelong food allergy. But it is also, in its way, a hopeful one. Because if the skin barrier is where the problem begins, then repairing and maintaining the skin barrier early in life, something that can be done with simple moisturizers, might be a way to reduce the risk of food allergy developing. Research into this possibility is ongoing. Several clinical trials have examined whether intensive moisturizing of infants with eczema, beginning shortly after birth, can reduce the rate of food allergy development. The results so far are encouraging, if not yet definitive. But the logic is compelling, and the intervention is safe, affordable, and simple. Sometimes the most powerful preventive tools are not complicated at all. Histamine is the molecule most people associate with allergies, and for good reason. It is the primary mediator released when mast cells degranulate, and it is responsible for the most immediate, classic allergic symptoms. But histamine is much more than just an allergy chemical. It is one of the most versatile signaling molecules in the entire body, playing roles in the nervous system, in digestion, in regulating the sleep-wake cycle, in stomach acid production, and in dozens of other processes. The human body produces histamine continuously, not just during allergic reactions. It is present in many foods, particularly fermented ones. Aged cheeses, wine, cured meats, and sauerkraut all contain significant amounts of histamine. Some people have difficulty breaking down dietary histamine efficiently, a condition called histamine intolerance, which can produce symptoms that resemble allergies, even without any IgE involvement at all. Antihistamines, the drugs taken by hundreds of millions of people every year to relieve allergy symptoms, work by blocking histamine receptors rather than by stopping histamine from being produced. There are several types of histamine receptor in the body, labeled H1, H2, H3, and H4, and they are found in different tissues and serve different functions. Most classic antihistamines target the H1 receptor, which is the one responsible for the sneezing, itching, and nasal congestion associated with hay fever and other allergic conditions. When an antihistamine occupies the H1 receptor, histamine can still be released by mast cells, but it cannot dock at the receptor and trigger symptoms. The first generation of antihistamines, developed in the 1940s, were effective but came with a significant side effect. They crossed the blood-brain barrier easily, which meant they also blocked H1 receptors in the brain. Since histamine plays an important role in maintaining wakefulness, blocking these receptors caused drowsiness. The sedating antihistamines like diphenhydramine are still sold today, still effective, and still responsible for the pleasant drowsiness that many people associate with taking allergy medicine before bed. The second-generation antihistamines, developed from the 1980s onward, were specifically designed to stay outside the brain. They are non-sedating, which makes them more suitable for daytime use, though some people find the older, drowsier varieties more effective and certainly more conducive to sleep. It is a peculiar thing to consider that one of the most taken medications in the world essentially works by blocking the same neurotransmitter the brain uses to tell itself to stay awake. Anaphylaxis is the most severe form of allergic reaction, and it is one of the most medically dramatic things the human body can do to itself. In anaphylaxis, the allergic response does not stay localized in the nose or the skin. It goes systemic. Mast cells throughout the body, in the skin, the airways, the gut, and critically, around blood vessels everywhere, all degranulate simultaneously. The result is a cascade of effects happening at once. Blood vessels throughout the body dilate. Fluid leaks out of blood vessels into surrounding tissues. Blood pressure drops. The airways can swell and constrict. Smooth muscle in the gut contracts. The heart may race or become arrhythmic. In severe cases, within minutes, the circulatory system can collapse to the point where the brain and vital organs begin to be deprived of oxygen. Despite how frightening this sounds and how genuinely dangerous anaphylaxis is, the body's response makes a certain terrible logic. Imagine a scenario deep in evolutionary time where what the immune system encounters is not a peanut protein, but a massive parasitic invasion or a venomous sting delivering toxins into the bloodstream. The systemic response, the immediate, whole-body mobilization, might have been the right answer. Flood the system with inflammatory signals. Purge everything through every available exit. Contract muscles to expel material from the gut. Increase vascular permeability to flood tissues with immune cells. In the right context, this is a survival response. In the context of a single peanut consumed at a birthday party, it is catastrophic. The treatment for anaphylaxis is epinephrine, also known as adrenaline. It works quickly and powerfully, counteracting the effects of histamine and the other mediators. It constricts blood vessels, raises blood pressure, relaxes the smooth muscle in the airways, and reverses most of the immediate dangerous effects within minutes. The modern epinephrine auto-injector, the device that millions of people with severe allergies carry with them at all times, is one of the genuine medical marvels of the 20th century. A spring-loaded syringe designed to be pressed against the outer thigh and activated in a single motion, usable by a frightened parent or a friend with no medical training, delivering a precisely measured dose of the one drug that can stop anaphylaxis in its tracks. The devices are simple enough in principle, but represent decades of engineering refinement aimed at a single goal, making it possible for a non-medical person to administer a life-saving drug in an emergency, quickly enough and reliably enough to matter. Pollen is one of the most beautifully designed objects in nature. Each grain is a marvel of miniature engineering, built not for the purpose of bothering human noses, but for the purpose of carrying genetic material from one plant to another. Plants cannot walk toward each other. They cannot seek out a mate, and yet they reproduce sexually, exchanging genetic information with other members of their species over distances that can range from a few meters to hundreds of kilometers. Pollen is their solution to this problem. It is a package, a tiny, armored vessel containing the male genetic material of a plant, designed to survive the journey through air, through insects, through wind, and arrive intact at a flower of the same species. The outer wall of a pollen grain, called the exene, is made of one of the toughest biological polymers known, sporopollenin. It is so resistant to degradation that pollen grains can survive in sediments for millions of years. Scientists who study ancient climates and vegetation patterns use pollen preserved in lake beds and bogs as a kind of biological record. Reading the history of plant communities and even past climates from these microscopic time capsules, a grain of pollen found in a core of sediment from a lake bed can tell a scientist what trees were growing in that region 10,000 years ago or 100,000 years ago. They are, in their way, ancient letters that the world wrote to itself and never stopped sending. The reason pollen triggers allergies so effectively is related to the proteins on its surface. These surface proteins are part of the pollen's biological function, involved in recognizing and communicating with flowers of the right species. But in sensitized individuals, it is these proteins that the immune system has learned to identify as threatening. When a pollen grain lands on the moist surface of the nasal lining or the eyes, it can dissolve slightly, releasing these proteins. Waiting IgE antibodies on the surface of mast cells recognize them instantly, and within seconds, the cascade begins. Different plants release pollen at different times of year, which is why allergy sufferers often experience symptoms that follow a reliable seasonal calendar. Tree pollens tend to dominate in early spring. Grass pollens peak in late spring and early summer. Weed pollens, and particularly the notorious ragweed, reign in late summer and autumn. For someone sensitized to all three, the allergy season can stretch across most of the year. Grass pollen is the single most common trigger of allergic rhinitis worldwide. There are thousands of species of grass on Earth, and they collectively cover more of the land surface than any other type of plant. Grasses grow on every continent, including Antarctica, in habitats ranging from tropical rainforests to Arctic tundra. They include the cereal crops that feed the world: wheat, rice, maize, barley, rye, and the lawn grasses of parks and gardens and the wild grasslands of every continent. They are, in terms of ecological dominance, one of the most successful plant families in the history of life on Earth. And their pollen, light enough to travel kilometers on the breeze, is the bane of hundreds of millions of people every spring and summer. What makes grass pollen particularly vexing as an allergen is not just its abundance, but its cross-reactivity. Many different grass species produce proteins so similar in structure that an immune system sensitized to one species will react to many others. Someone allergic to Timothy grass pollen, a common pasture grass, will often also react to ryegrass, meadowgrass, orchard grass, and dozens of other species. Because their pollen proteins are similar enough to trigger the same IgE antibodies. This cross-reactivity means that avoiding exposure to the specific species you are sensitized to is nearly impossible. The proteins are everywhere. Cross-reactivity extends beyond just different grass species. It is one of the most peculiar phenomena in all of allergy science. The proteins that pollen uses to communicate with flowers are sometimes structurally similar to proteins found in foods. A person with a birch tree pollen allergy, for example, may find that they react to apples, carrots, celery, hazelnuts, and almonds. This is called oral allergy syndrome or pollen food allergy syndrome. It is not a true food allergy in the classical sense. It does not involve the gut immune system. It is simply a case of proteins in these foods resembling, closely enough, the pollen proteins that the immune system has already memorized. The symptoms of oral allergy syndrome are usually mild, a tingling or itching in the mouth and lips and throat when the offending food is eaten, resolving within minutes. The proteins responsible are usually destroyed by heat, which is why people with oral allergy syndrome can often eat cooked versions of the foods they react to raw. A person who cannot eat a raw apple without their mouth tingling may be able to eat apple pie or apple sauce without any problem at all. The cooking has broken down the offending protein structure, and the immune system no longer recognizes it as the enemy. It is a reminder of how exquisitely the immune system operates at the level of molecular shape. It is not reading the word apple and deciding to react. It is reading a specific three-dimensional protein structure and comparing it against its library of memorized threats. When the protein is changed even slightly by heat, the match no longer occurs and peace is restored. Dust mites are among the most common indoor allergen sources in the world, and most people have very little idea what they actually are. They are not insects. They are arachnids, related to spiders and ticks, though they are microscopic. A single dust mite measures roughly 1/4 to 1/3 of a millimeter in length, far too small to see with the naked eye. They live in the warm, humid microenvironments found in mattresses, pillows, upholstered furniture, and carpets, places where human skin flakes, their primary food source, accumulate. A typical mattress that has been in use for several years may contain millions of dust mites, coexisting invisibly with the person who sleeps in it every night. They are, by any measure, successful organisms. They have no need for water beyond the humidity they absorb from the air. They feed on shed human skin, which is available in unlimited supply in any occupied home. They reproduce rapidly and thrive in the temperatures that humans find comfortable. From the dust mite's perspective, the human bedroom is paradise. The allergen produced by dust mites is not the mites themselves, but their feces. Dust mite fecal particles are roughly 10 to 20 micrometers in diameter, small enough to become airborne when disturbed, small enough to be inhaled deep into the airways. These particles contain enzymes, proteins the mites use for digestion, and it is these proteins that act as allergens. When someone sensitized to dust mites inhales these particles, the immune response follows: sneezing, nasal congestion, itching eyes. For the roughly 20% of the world population sensitized to dust mites, simply sleeping in an ordinary bed is a nightly exposure to their primary allergen. Dust mite populations can be reduced, though not eliminated, by encasing mattresses and pillows in allergen-impermeable covers, washing bedding regularly in hot water, reducing indoor humidity, and replacing carpets with hard flooring. These measures do not create a mite-free environment, but they can significantly reduce the allergen burden in the air where someone sleeps. And for sensitive individuals, even a modest reduction can translate into meaningfully better sleep and fewer symptoms. The eyes are particularly vulnerable to allergens because they are perpetually exposed. Unlike the airways, which have the nose as a first filter, the surface of the eye, the conjunctiva, is directly in contact with the outside world. When airborne allergens land on this surface, they encounter a tissue rich in mast cells and well stocked with the IgE antibodies of sensitized individuals. The resulting condition is called allergic conjunctivitis. The classic presentation, red, itchy, watering eyes, is familiar to anyone who has experienced it. It ranges from mildly annoying to genuinely disabling in severe cases. What makes allergic conjunctivitis interesting from a scientific standpoint is how closely the eye is connected to the nose, not just anatomically through the tear duct, but immunologically. The mucosal immune system of the eyes and nose are in close communication. Treating nasal allergy with a nasal steroid spray often also improves eye symptoms, even though the medication never touches the eyes. The immune tissues along this surface are so interconnected that calming inflammation in one area sends calming signals that affect the other. The characteristic itch of allergic conjunctivitis is particularly intense because the conjunctiva is unusually densely innervated, meaning it has a very high concentration of nerve fibers. Histamine, released from mast cells in the conjunctiva, stimulates these nerve fibers directly. The resulting itch is one of the most compelling and difficult to resist itches the human body produces. Rubbing the eyes in response is instinctive, but it is also counterproductive, since rubbing mechanically degranulates more mast cells and intensifies and prolongs the reaction. Every person who has ever suffered through seasonal allergies has learned, sometimes repeatedly, that rubbing makes it worse. The knowledge rarely stops the impulse. The nasal passages are among the most remarkable and underappreciated structures in the human body. They are not simply tunnels carrying air to the lungs. They are a complex, actively managed system for conditioning incoming air. The nasal lining warms air to body temperature, humidifies it to near 100% relative humidity, and filters it through a carpet of tiny hair-like structures called cilia, which move constantly, sweeping particles caught in a layer of mucus toward the throat to be swallowed and neutralized by stomach acid. The nasal turbinates, those curved shelves of bone covered in mucous membrane inside the nose, dramatically increase the surface area available for this air conditioning, creating a convoluted pathway that slows air down and ensures maximum contact with the conditioning surface. This system works beautifully under normal conditions. In allergic rhinitis, which is the technical name for hay fever, the immune response disrupts it profoundly. Histamine and other mediators cause the blood vessels in the nasal lining to dilate and become leaky. The tissue swells. Mucus production increases dramatically. The cilia, overwhelmed by the volume of secretions, struggle to keep up. The nose becomes congested, runny, and seemingly determined to make its owner miserable. The word rhinitis simply means inflammation of the nose, rhino being the Greek root for nose. And indeed, The inflamed, swollen nasal lining in a severe allergic reaction is a miniature example of the same inflammatory process that happens in joints, in arthritis, in the bowel, in inflammatory bowel disease, in the skin, in eczema. Inflammation is one of the immune system's most powerful tools, but it is not a precise one. When it is deployed in the right place at the right time against a genuine threat, it saves lives. When it is deployed against a harmless pollen grain in the delicate lining of the nose, it produces misery. The nose is also deeply connected to the sense of smell, of course, and chronic nasal congestion from persistent allergic rhinitis does more than block breathing. It reduces or eliminates the sense of smell, which in turn dramatically reduces the sense of taste, since most of what we experience as flavor is actually aroma, reaching the olfactory receptors through the back of the nasal cavity. People with year-round allergic rhinitis often describe food as tasting flat, lifeless. The world smells of nothing. This is not a trivial quality of life issue. Smell and taste are deeply intertwined with memory, with pleasure, with appetite. Chronic loss of these senses can affect mood, diet, and well-being in ways that are easy to underestimate. The connection between allergies and the brain is more direct than many people realize. The same cytokines, the same inflammatory signaling molecules that mediate allergic reactions in the body, can cross into the brain or signal to it through various pathways, and there they can affect mood, cognition, and behavior. Many people with seasonal allergies report a cognitive fog during peak pollen season that goes beyond just the inconvenience of sneezing. Difficulty concentrating, mental slowness, a vague sense of being not quite sharp. Research has supported this impression. Studies using objective cognitive testing have found measurable differences in certain cognitive tasks during high allergen exposure compared to low allergen exposure in sensitized individuals. Whether this is purely the result of poor sleep from congestion, or whether the inflammatory mediators themselves are affecting brain function directly, or both, is still being worked out. What is increasingly clear is that the immune system and the brain are not separate systems that politely stay out of each other's territory. They are deeply interconnected. Immune cells are found in the brain. The brain monitors immune status through dedicated sensing pathways. Cytokines produced during immune responses reach the brain and alter its activity. The classic sick feeling of a flu, the fatigue, the low mood, the desire to do nothing but lie still and rest, is not caused by the virus directly, but by the cytokines the immune system produces in fighting the virus. A similar, milder version of this same process may contribute to the fatigue and brain fog of allergy season. Asthma is the allergic disease of the airways, and it is one of the most common chronic conditions in the world. Roughly 300 million people have asthma globally. It is characterized by reversible airway obstruction. The airways become inflamed, the smooth muscle surrounding them contracts, and mucus production increases. Breathing becomes difficult, labored, accompanied in many cases by the characteristic wheeze as air is forced through narrowed passages. Allergic asthma, triggered by allergen exposure, is the most common form, accounting for the majority of asthma cases in children. The same IgE-mediated mast cell mechanism that drives hay fever operates in the airways. Inhaled allergens, dust mite particles, animal dander, mold spores trigger mast cells lining the airway to degranulate. But in the lungs, with their branching passages and narrow diameters, the swelling and mucus and smooth muscle contraction that follow are not just unpleasant, they can reduce airflow to dangerous levels. The lungs are, structurally, an extraordinary organ. From the point where the windpipe divides into the two main bronchi, the airways branch and branch again, becoming narrower and more numerous at each division, until they end in hundreds of millions of tiny air sacs called alveoli, each one wrapped in a delicate net of capillaries. The total surface area of the lungs is roughly the size of a tennis court, a fact that mirrors the gut and underscores how both surfaces face the challenge of interfacing the inside of the body with the outside world across a vast, thin, permeable barrier. In asthma, this intricate architecture is compromised. The narrowing of the airways, even slightly, has an outsized effect on airflow because the resistance to airflow through a tube increases as the fourth power of any reduction in radius. A modest swelling that reduces an airway's diameter by half increases its resistance to airflow by 16 times. The geometry works against the asthmatic. The modern management of asthma is built around two types of medication: relievers, typically short-acting bronchodilators that relax airway smooth muscle quickly, providing rapid symptom relief, and preventers, typically inhaled corticosteroids that reduce the underlying inflammation over time. The inhaled corticosteroid was one of the great medical breakthroughs of the 20th century for asthma, delivering anti-inflammatory medication directly to the inflamed surface at doses far lower than would be needed if taken systemically, with minimal side effects, and with the ability to transform the daily experience of living with asthma. People who were previously hospitalized repeatedly for dangerous attacks can, with consistent preventer therapy, lead lives largely unaffected by their condition. Eczema, known medically as atopic dermatitis, is often the first allergic disease to appear in a person's life, which is why it is sometimes described as the entry point into what allergists call the atopic march. This is the observed tendency for allergic diseases to develop in a particular sequence, beginning with eczema in infancy, progressing in some individuals to food allergies, then allergic rhinitis, then asthma, as the child grows. Not everyone with eczema follows this path, and not every asthmatic had eczema first. But the pattern is real and consistent enough to suggest that the underlying immune dysregulation that causes one allergic condition creates conditions that make others more likely. The word atopy, used to describe the underlying tendency to develop allergic diseases, comes from the Greek atopos, meaning strange or out of place. It was coined in the 1920s to describe this inherited tendency of the immune system to make IgE against harmless environmental substances. Atopic individuals make more IgE overall. Their mast cells and basophils are more reactive. The threshold for triggering a response is lower. This is not a disease in itself. It is a biological tendency, a particular setting on the immune system, one that likely conferred some advantage in environments where parasite exposure was constant. But that creates vulnerabilities in the modern world. Eczema itself is a chronic, inflammatory skin condition rooted in a defect in the skin barrier. The skin is normally maintained by a complex arrangement of proteins, fats, and tightly packed cells that form a near-impermeable barrier. In eczema, mutations in a gene called filaggrin, which codes for a protein essential to the structural integrity of the skin surface, mean that the barrier is leaky. Water escapes more easily, leaving the skin dry. Substances from the outside world penetrate more easily. The immune system beneath the skin, alerted by the disruption of the barrier and by the unusual proteins entering through it, mounts an inflammatory response. The result is the red, itchy, inflamed, and perpetually uncomfortable skin of eczema. Managing eczema is a constant, careful practice. Moisturizing the skin several times daily to compensate for the barrier's water retention failure. Avoiding soaps and detergents that strip the remaining lipid barrier. Identifying and avoiding environmental triggers. Using topical anti-inflammatory medications judiciously during flares. It requires patience and consistency rather than any single dramatic intervention, which makes it, for many sufferers, one of the more emotionally exhausting of the allergic diseases to live with. The chronic, relentless nature of the itch is particularly difficult. Itching activates the same reward pathways in the brain as scratching, creating a cycle that is physiologically reinforcing, even as scratching worsens the skin damage and prolongs the flare. Contact dermatitis is a form of allergic reaction that is different in a fundamental way from the classic hay, fever, or food allergy most people picture when they think of allergies. It does not involve IgE at all. It involves a completely separate arm of the immune system, one mediated not by antibodies but by a class of white blood cells called T lymphocytes. The reaction is slower. Where an IgE-mediated reaction can occur within seconds of allergen exposure, allergic contact dermatitis takes anywhere from 12 to 72 hours after contact to develop. This delay is why it is called a delayed type hypersensitivity reaction, and understanding this distinction matters, because the mechanism is different, the triggers are different, and the treatment approaches overlap only partially with those used for classic allergic disease. The most famous cause of allergic contact dermatitis in the world is urushiol, the oil produced by poison ivy, poison oak, and poison sumac. These plants belong to the same botanical family and all produce urushiol in their leaves, stems, and roots. The reaction to urushiol follows the classic delayed pattern. First contact with the plant causes sensitization without visible reaction. On subsequent contacts, the sensitized T cells recognize urushiol-modified proteins in the skin and mount a response. The result is the intensely itchy, blistering rash that anyone who has encountered poison ivy in a forest or a garden knows all too well. What makes urushiol particularly remarkable as an allergen is how extraordinary its potency is. The amount needed to cause a reaction in a sensitized person is vanishingly small. It has been calculated that roughly 1/4 milligram of urushiol, an amount invisible to the naked eye and lighter than a single grain of table salt, is enough to provoke a reaction in a sensitive individual. A single poison ivy plant contains enough urushiol to sensitize roughly 500 people. It can remain potent on tools, clothing, or pet fur for years. There are documented cases of people reacting to urushiol residue on tools stored in a garage that had not been used for a decade. Other common causes of allergic contact dermatitis include nickel, the most common metal allergen and the reason why many people cannot wear cheap jewelry or jeans with metal buttons. Fragrance compounds used in perfumes and skincare products. Preservatives in cosmetics. Rubber chemicals in latex gloves. Hair dye chemicals, particularly a compound called paraphenylnediamine, which is the primary allergen in most permanent hair dyes. Each of these causes a reaction through the same delayed T-cell mechanism, though the specific T-cell population involved and the exact molecular events differ in detail between different contact allergens. Identifying the cause of allergic contact dermatitis requires a diagnostic procedure called patch testing, which is methodologically almost the opposite of the skin prick test used for IgE-mediated allergies. In patch testing, small panels of suspected allergens in standardized concentrations are applied to the skin under adhesive patches and left there for 48 hours. When the patches are removed and the skin assessed 24 to 48 hours later, a positive result shows as a localized area of redness and swelling at the site of the specific allergen. The pattern of positive reactions, combined with the history of when and where the rash appeared, allows the clinician to identify the culprit. Patch testing is painstaking work, and the panels can include dozens of substances. But when a positive result is identified and the person is able to successfully avoid the allergen, the improvement can be dramatic and complete. Latex allergy is a particularly instructive example of how a new allergen can emerge in a population in a short period of time and then decline again as practices change. Natural rubber latex comes from the Hevea brasiliensis tree, cultivated primarily in Southeast Asia. It has been processed into gloves and medical equipment for over a century. For most of that time, latex allergy was rare. Then, in the late 1980s and through the 1990s, following the widespread adoption of universal precautions in healthcare settings in response to the HIV epidemic, the use of latex gloves exploded. Suddenly, healthcare workers were wearing latex gloves for many hours a day, every workday, for years. Rates of latex sensitization in healthcare workers rose sharply. Rates of anaphylaxis in operating rooms increased. Patients with certain risk factors, particularly those who had undergone multiple surgeries, were found to have elevated sensitization rates. The solution was to change practices. Powdered latex gloves were identified as a particular problem because the powder aerosolized latex proteins, carrying them into the air and allowing inhalation as well as skin contact. Powdered latex gloves were phased out. Latex-free alternatives, nitrile and vinyl gloves, became widely adopted. Over the following decade, rates of latex sensitization in healthcare workers declined. The epidemic of latex allergy that had arisen from a change in practice largely resolved through another change in practice. It is a demonstration that allergen burden matters, that the level of exposure, the frequency, the route, the cumulative dose can determine whether sensitization occurs, and that reducing exposure can prevent sensitization in those not yet sensitized, even while those already sensitized must continue to avoid the allergen carefully. Latex allergy also has a notable cross-reactivity story. Certain foods, particularly banana, avocado, kiwi, and chestnut, share proteins with natural rubber latex that are similar enough to cross-react. People with latex allergy are warned about this, and those with severe latex allergy may need to avoid these foods. It is another example of the immune system's molecular pattern recognition, creating an unexpected bridge between what seems like an entirely unrelated substance in the environment and a food, linked only by the accident of evolutionary convergence in protein structure. Eosinophils are a type of white blood cell whose name comes from their affinity for a red laboratory dye called eosin. Under a microscope, they stain a vivid pink, making them easy to identify. They are normally present in the blood in small numbers, less than 5% of circulating white blood cells. In tissues, they are found primarily in the gut lining, where they are thought to play a role in defense against parasites. In allergic disease, eosinophil numbers in both blood and tissues can rise substantially. They accumulate at the sites of allergic inflammation, in the airways, in asthma, in the skin, in eczema, in the nasal lining, in allergic rhinitis. Eosinophils are not simply bystanders at these sites. They are active participants in the inflammatory process. They release a range of toxic proteins and reactive oxygen species designed, in evolutionary terms, to destroy parasites. These weapons are not particularly precise, and when deployed in the airways or the gut or the skin, they contribute to tissue damage and inflammation. In severe eosinophilic asthma, the accumulation of eosinophils in airway tissue leads to mucus plugging, airway remodeling, and a progressive loss of lung function that goes beyond simple inflammation. Treating the eosinophilic component with biologics targeting interleukin-5, the primary survival and activation signal for eosinophils, can dramatically reduce eosinophil numbers and improve outcomes in these patients. There is also a spectrum of conditions called eosinophilic gastrointestinal disorders, in which eosinophils accumulate in the lining of the esophagus, stomach, or intestines in numbers far above normal, causing inflammation and tissue damage. Eosinophilic esophagitis is the most common of these and has been increasingly recognized over the past 2 decades. It causes difficulty swallowing, food getting stuck, chest pain, and in untreated cases, progressive scarring and narrowing of the esophagus. It is often, though not always, driven by food allergens reaching the esophageal surface. The immune response there is not a rapid IgE-mediated one, but a more chronic, eosinophil-driven process that plays out over weeks to months of repeated exposure. Treatment involves identifying and eliminating trigger foods, using swallowed topical steroids to reduce esophageal inflammation, or in some cases, using biologics. It is a condition that was almost entirely unrecognized 20 years ago and is now one of the most actively researched areas in allergy gastroenterology. The relationship between stress and allergic disease is real, measurable, and often underappreciated in clinical settings. Psychological stress, does not cause allergies. A person who is not immunologically primed to react to cat dander will not develop a reaction simply because they are stressed. But in a person who is already sensitized, stress can meaningfully influence the severity and frequency of allergic reactions. This is not psychosomatic in the dismissive sense sometimes meant by that word. It reflects genuine biological connections between the nervous system, the endocrine system, and the immune system. The stress response is mediated primarily by two hormones: adrenaline, released immediately by the adrenal medulla in response to acute stressors, and cortisol, released over a longer timescale by the adrenal cortex in response to sustained stress. Cortisol, in its normal physiological role, is actually anti-inflammatory. This is why it and its synthetic derivatives are widely used as treatments for inflammatory conditions, including asthma and eczema. Short-term elevation of cortisol during acute stress tends to temporarily suppress immune activity, but chronic, sustained stress leads to a different picture. Prolonged cortisol exposure can cause the immune system to become relatively resistant to cortisol's anti-inflammatory signals. Cells that normally respond to cortisol by damping down inflammation begin to respond less effectively. The result can be a net increase in inflammatory tone, making allergic reactions more severe and more difficult to control. Beyond cortisol, stress activates neuropeptides and neurotransmitters that directly influence mast cells. Mast cells have receptors for stress-related signaling molecules, including substance P and corticotropin-releasing hormone. Activation of these receptors can lower the threshold for mast cell degranulation, making them more reactive than they would otherwise be. This is one of the reasons that allergic symptoms, including urticaria and asthma, can worsen at times of psychological stress, even when allergen exposure has not changed. The trigger has not changed, but the system is primed to respond more vigorously. Understanding this connection does not mean that telling someone with severe asthma to simply reduce their stress will solve their problem, but it does underscore the importance of treating the whole person. Sleep quality, mental health support, stress reduction where possible, these are not luxury add-ons to allergy management. They are components of the same system and contribute to outcomes in ways that are biologically grounded. Pregnancy creates a fascinating and delicate immunological situation. The fetus carries genetic material from the father that is foreign to the mother's immune system. In any other context, foreign cells introduced into the body would be attacked and destroyed. The immune system must therefore undergo significant adjustments during pregnancy to tolerate the developing child without abandoning its capacity to protect against genuine pathogens. These adjustments involve shifts in the balance between different immune cell populations and changes in the types of immune responses that dominate. One effect of these shifts is on allergic disease. Many women with allergies or asthma notice changes in their symptoms during pregnancy. The pattern varies. Roughly 1/3 of women with asthma experience their asthma worsening during pregnancy. 1/3 find it improves, and 1/3 notice little change. The hormonal environment of pregnancy, particularly elevated levels of progesterone and estrogen, influences immune function in complex ways. The same shift toward immune tolerance that protects the fetus may, in some women, reduce allergic reactivity. In others, the changes may favor conditions that worsen allergic inflammation. Nasal congestion, which is common in pregnancy even without allergic rhinitis due to hormonally driven vascular changes, can compound allergy symptoms that were already present. The immune environment of pregnancy also shapes the developing immune system of the fetus. What the mother encounters, how her immune system responds to her environment, what inflammatory and regulatory signals circulate during gestation, all of this influences the epigenetic programming of the fetal immune system. Children born to mothers with allergies are more likely to develop allergies themselves. And while genetics explains part of this, the in utero immune environment contributes independently. The very first immune education a person receives begins before birth. Urticaria, commonly called hives, is one of the most immediately dramatic manifestations of allergic and immune dysfunction. The characteristic lesions, raised, pale in the center, red at the edges, intensely itchy, appearing suddenly and moving around the body, appearing in one place and fading while new ones emerge elsewhere, are the result of mast cells in the superficial skin releasing histamine and causing localized leakage from the small blood vessels just below the skin surface. The fluid that leaks into the tissue creates the raised wheal. The surrounding redness is the dilated blood vessels. The itch is histamine, stimulating nerve endings. Acute urticaria, lasting less than 6 weeks, is most commonly caused by allergic reactions to foods, medications, or insect stings, or by viral infections. It is alarming when it appears, but usually resolves as the triggering agent is eliminated or the infection clears. Chronic urticaria, defined as hives occurring on most days for more than 6 weeks, is a different and often more difficult condition. In the majority of chronic urticaria cases, no external allergen trigger can be identified. The mast cells are activating spontaneously, without an obvious external cause. This form is called chronic spontaneous urticaria, and the mechanism in many cases appears to involve autoimmune factors. Antibodies targeting the mast cells themselves or targeting the IgE receptor on their surface, causing spontaneous degranulation. The condition can persist for years and has a profound impact on quality of life, with the constant, unpredictable itching disrupting sleep, concentration, and daily functioning. The same biologic, omalizumab, that was developed to block IgE for allergic asthma has proven highly effective for chronic spontaneous urticaria, producing complete or near-complete resolution of hives in the majority of patients who had failed to respond to standard antihistamine therapy. It is another example of the way understanding the molecular mechanisms of immune disease opens therapeutic pathways that would otherwise be invisible. Without the knowledge that IgE plays a role in chronic spontaneous urticaria, the idea of using a drug that targets IgE would never have arisen. With that knowledge, a drug designed for one condition becomes transformative for another. The airways, those branching passages that carry air from the nose and mouth down through the trachea and into the vast labyrinth of bronchi, bronchioles, and alveoli, have their own immune system that is distinct in important ways from the systemic immune system in the blood. The respiratory mucosa is lined with a layer of mucus that traps inhaled particles, and beneath it, a layer of cells that are not just passive bystanders, but active immune sensors. These epithelial cells express pattern recognition receptors that detect signs of damage or infection. When they are stressed, whether by a virus, a pollutant, or an allergen, they release signaling molecules called alarmins. The most studied of these are interleukin 2-5, interleukin 3-3, and thymic stromal lymphopoietin. These alarmins are among the earliest signals in the allergic cascade in the airways. They are released by epithelial cells that sense something is wrong before any adaptive immune response has had time to develop. They activate a class of cells called innate lymphoid cells type 2, which respond by producing large amounts of the cytokines interleukin 4, interleukin 5, and interleukin 1-3, the very same cytokines that drive allergic inflammation downstream. The alarmins are, in effect, the immune system's first responders, the cells that set the inflammatory tone before the more specific, slower adaptive immune system has assembled its response. This innate immune component of allergic disease has only become well understood in the past decade. It helps explain why certain environmental factors, particularly air pollution and tobacco smoke exposure, seem to amplify the risk and severity of allergic airway disease, even without directly triggering an adaptive immune response themselves. Pollutants can damage airway epithelial cells, triggering alarmin release, creating an inflammatory environment that primes the immune system to respond more vigorously to subsequent allergen encounters. The epithelium is not just a barrier. It is a sensor and a communicator, constantly reading the environment and broadcasting its assessment to the immune cells waiting below. The biosphere, the living layer of the Earth, produces pollen in quantities that are almost impossible to visualize. A single ragweed plant, a common weed across much of North America, can produce approximately 1 billion pollen grains in a single season. There are tens of millions of ragweed plants across North America. The pollen produced is so light that it has been detected in the atmosphere more than 400 kilometers out to sea and at altitudes of several kilometers. Individual pollen grains can remain airborne for days, carried by weather systems across entire continents. During peak ragweed season in late summer and early autumn, the air in affected regions contains pollen in concentrations that can reach tens of thousands of grains per cubic meter of air. Climate change is altering pollen seasons in ways that are measurable and concerning for allergy sufferers. Warmer temperatures and earlier springs mean that pollen seasons are starting earlier in the year. Higher carbon dioxide concentrations in the atmosphere accelerate plant growth and increase pollen production. Warmer autumn temperatures mean that ragweed and other weed pollens persist later in the year before the first frosts kill the plants. Studies tracking pollen seasons over the past several decades have found that in many regions of North America and Europe, the pollen season has extended by 2 to 4 weeks compared to the middle of the 20th century. The total amount of pollen produced annually has increased substantially. For the roughly 500 million people worldwide with allergic rhinitis, this means longer, more intense, and harder to manage allergy seasons. This is not just an inconvenience. Pollen seasons that extend later into autumn also increasingly overlap with the beginning of the school year and with the typical peak of respiratory virus season. For children with allergic asthma, the autumn combination of peak mold, spore release from decomposing leaves, sustained ragweed and grass pollen, and the beginning of the cold and flu season is one of the most dangerous periods of the year for asthma attacks. Hospitals in many countries see a predictable September and October spike in pediatric asthma admissions that corresponds almost precisely with this convergence. Understanding and predicting these patterns helps clinicians advise patients and families to be proactive, to maximize preventer therapy, to have reliever medication accessible, to monitor symptoms more carefully during the dangerous weeks. The molecular biology of how the immune system decides whether to mount a protective response or a tolerant one to a new substance is extraordinarily intricate. At the center of the decision is a class of immune cells called dendritic cells. These are the master antigen-presenting cells, the cells whose job it is to sample the environment, capture foreign substances, process them into small molecular fragments, and present those fragments to naive T cells. The dendritic cell is, in a sense, the translator between the outside world and the adaptive immune system. It is the cell that decides what story to tell about what it has found. When a dendritic cell picks up an allergen, the nature of the signal it sends to the T cell it interacts with depends enormously on the context in which the encounter occurred. What other signals were present when the dendritic cell captured the allergen? Was there evidence of tissue damage? Were there alarmins present? Were there bacterial products indicating infection? Or was the encounter calm in a tolerogenic environment without any signals of danger? In a tolerogenic environment, the dendritic cell presents the allergen to a T cell in a way that tends to generate regulatory T cells, cells that produce anti-inflammatory cytokines and actively suppress immune responses to that substance. The gut is rich in this kind of tolerogenic environment. The gut dendritic cells are exposed to constant, vast quantities of food antigens. They have been shaped by evolution and by the microbial environment to default toward tolerance rather than inflammation for anything that arrives through this route. It is this gut-mediated tolerance that immunotherapy is essentially trying to recapitulate through gradual, escalating oral exposure. In an inflamed or damaged environment, the same dendritic cell presenting the same allergen is likely to generate a very different T cell response. One that tips toward the type 2 response, toward IgE production, toward allergic sensitization. The allergen is the same. The dendritic cell is the same. The T cell is the same. Only the context has changed, and yet the outcome is entirely different. This context dependence of immune decision-making is beautiful and somewhat dizzying. The immune system is not reading just the antigen. It is reading everything. The environment, the cellular signals, the tissue context, the history of prior encounters. It is making decisions based on all of this simultaneously, in real time, at the level of molecular interactions that happen in milliseconds. There is a class of allergic reaction that does not follow the IgE pattern at all, and that is often referred to as non-allergic hypersensitivity, or in some cases, intolerance. Aspirin and other non-steroidal anti-inflammatory drugs can trigger reactions in a subset of people that resemble allergic reactions in their symptoms, but are not mediated by IgE. These reactions occur because these drugs inhibit an enzyme called cyclooxygenase, which changes the balance of inflammatory signaling in the body in a way that, in susceptible individuals, shifts too much toward the production of leukotrienes, another class of inflammatory mediators. The resulting symptoms, nasal congestion, bronchospasm, and in severe cases hives and anaphylaxis-like reactions, are real and can be severe. But the mechanism is pharmacological rather than immunological. The immune system has not been sensitized. There are no antibodies involved. It is a direct chemical effect of the drug on a particular biological pathway. Similarly, certain foods trigger reactions in some people through mechanisms that do not involve the immune system directly. Histamine intolerance, already mentioned, is one example. Another is reactions to sulfites, preservatives found in wine, dried fruit, and some processed foods, which can trigger asthma and other symptoms in susceptible individuals through mechanisms that include, but are not limited to, IgE-mediated allergy. Food dyes, salicylates, tyramine in aged foods. The range of non-immunological food sensitivities is broad and often confusing, both for patients and for clinicians, because the symptoms overlap substantially with those of genuine IgE-mediated food allergy. Distinguishing true food allergy from food intolerance matters for several reasons. True IgE-mediated allergy carries a risk of anaphylaxis that intolerance does not. The management of true allergy requires strict avoidance of even traces of the food, while many intolerances involve a dose threshold below which the person can consume the food without symptoms. And the diagnostic approach differs. IgE testing and oral food challenges are appropriate for evaluating true allergy. Different elimination and reintroduction approaches may be needed for intolerances. Conflating them leads to over-restriction of diet without achieving safety, or under-caution about genuinely dangerous allergens. Insect venom allergy is one of the most medically significant allergic conditions because the reactions it causes tend to be among the most severe and least predictable. Bee, wasp, hornet, and ant venom all contain proteins capable of triggering IgE-mediated sensitization. For most people, a sting causes local pain, redness, and swelling lasting a few days. This is a normal inflammatory response to injected venom, not an allergic one. For the roughly 3% of adults who have developed IgE sensitization to venom proteins, the same sting can trigger reactions ranging from large local reactions extending well beyond the sting site to systemic urticaria to full anaphylaxis. What makes insect venom allergy particularly anxiety-inducing is its unpredictability. The severity of a reaction cannot be reliably predicted from one sting to the next, even in the same individual. Someone who has had only a moderate systemic reaction in the past can, on a subsequent sting, develop life-threatening anaphylaxis. The dose of venom delivered varies with the species, the individual insect, and the circumstances of the sting. The current state of the person's immune system on the day of the sting plays a role. Whether they have been recently ill, whether they are taking certain medications, even exercise near the time of a sting can amplify reactions. Venom immunotherapy is one of the most effective forms of allergen immunotherapy available. When administered over the standard course, it reduces the risk of a systemic reaction to a sting from roughly 60% in untreated, sensitized individuals to under 5% in those who have completed the course. For someone who works outdoors, who spends time in gardens or forests, or who simply lives with the knowledge that the next bee sting could send them to hospital, this reduction in risk is transformative. It allows people to go outside without the background fear that has accompanied every summer excursion since the first severe reaction. It gives back a piece of the world. Your body right now, while you read these words and let your breathing slow and your thoughts drift, is at work in 100 invisible ways. Somewhere in your bone marrow, new immune cells are being born from stem cells, their identities still undetermined, waiting to be directed into the specific lineages the immune system needs. Somewhere in a lymph node, a dendritic cell is presenting information to a T cell, a small molecular dialogue determining whether a response is needed or whether the situation calls for patience and tolerance. Somewhere in your gut, a bacterium is producing a molecule that crosses the gut wall and reaches an immune cell and says, quietly, "Everything is fine here. Carry on." In someone with a well-controlled allergy, these processes run alongside the managed knowledge of what to avoid and how to treat symptoms when they arise. The immune system is not cured of its tendency toward allergic reactivity, not in most cases, but it is managed, navigated, worked with, rather than against. The mast cells still carry their IgE. The memory cells still hold their instructions, but exposure is reduced, or symptoms are treated when they arise, or, in the best cases, immunotherapy has shifted the balance enough that the alarm now rings more softly, or does not ring at all. There is a particular kind of resilience in living with a condition that requires constant management. People who carry epinephrine auto-injectors, who read ingredient labels as a matter of survival, who negotiate with restaurants about cross-contamination, who plan their outdoor activities around pollen forecasts and weather conditions, learn a kind of careful, attentive relationship with their environment that most people never need to develop. They become experts in their own biology, in a way that is, in its own way, something to respect. They learn, perhaps more clearly than most, that the boundary between the self and the world is not a wall. It is a negotiation, a constant, mostly invisible, occasionally dramatic exchange between the body and everything it moves through. Immunotherapy is one of the most elegant concepts in allergy treatment, and arguably the only one that addresses the underlying cause rather than just managing the symptoms. The idea is ancient and simple in principle. Expose the immune system to very small, gradually increasing amounts of an allergen, and over time, the immune system will learn to tolerate it rather than react against it. The process takes months to years. The doses begin tiny, far too small to trigger a significant reaction, and increase slowly, gradually, acclimatizing the immune system to the presence of the substance. The goal is not temporary suppression of symptoms, but long-term, durable change in how the immune system responds. Genuine tolerance. The mechanism by which immunotherapy induces tolerance involves several interconnected changes in the immune system. IgE levels against the allergen often fall over time. IgG antibodies, which can act as blocking antibodies, compete with IgE for the allergen and reduce its ability to trigger mast cells. Regulatory T cells, a class of immune cell whose job is to calm and regulate immune responses, increase in number and activity. The balance shifts from a reactive, alert immune posture toward a tolerant, calm one. It is, in effect, a re-education of the immune system. A long, patient process of teaching it that the thing it feared is not actually dangerous. The first clinical use of this approach for allergies was in 1911, when two British physicians named Leonard Noon and John Freeman began injecting patients with hay fever with tiny amounts of grass pollen extract. They observed that patients who received these injections experienced reduced symptoms during pollen season compared to those who did not. They did not know the mechanism, did not know about IgE, did not know about mast cells or any of the molecular machinery underlying the allergy. They simply observed that small, repeated exposures changed the response. Their work was a century ahead of the molecular science that would eventually explain why it worked. Modern allergen immunotherapy is far more refined. Subcutaneous immunotherapy, given by injection, remains the most established form. Sublingual immunotherapy, where drops or tablets containing the allergen are held under the tongue and absorbed through the oral mucosa, has become widely used, particularly in Europe, as a more convenient alternative that can be administered at home after the initial supervised doses. For specific allergies, including grass pollen, house dust mite, and cat dander, sublingual immunotherapy has strong evidence behind it. Oral immunotherapy for food allergies, particularly peanut, is now approved and available, allowing peanut-allergic individuals to desensitize themselves to peanut over a period of months, reducing their risk from accidental exposure. These are not perfect treatments. They require commitment, careful dosing, and ongoing maintenance. But they offer something that no antihistamine or nasal spray does: the possibility of change. The role of the gut microbiome in allergy is one of the most rapidly evolving areas of research in all of medicine. The microbiome, the community of trillions of microorganisms living in the gut, is not a passive resident. It is an active participant in immune development and immune regulation. From the very earliest days of life, the gut microbiome communicates intensively with the developing immune system. It produces metabolites, short-chain fatty acids, and other molecules that directly influence the development and function of immune cells. It helps calibrate the balance between inflammatory and regulatory immune responses. It is, in a very real sense, part of how the immune system learns to distinguish friend from foe. Disturbances to the gut microbiome in early life, particularly during the first months and years when the immune system is undergoing its most critical developmental phases, are associated with increased risk of allergic disease. Babies born by caesarean section who receive their initial microbiome from the hospital environment rather than from passing through the birth canal have higher rates of allergic diseases than those born vaginally. Babies fed formula rather than breast milk, which contains its own set of microbiome-supporting compounds, have different microbiome compositions and, in some studies, higher rates of allergy. Antibiotic use in early childhood, which can dramatically and sometimes persistently alter the gut microbiome, is associated with increased allergy risk in some studies, though the relationship is complex. The microbiomes of children who develop allergies tend to be less diverse than those of children who do not. This is not a simple relationship, and the direction of causality is not always clear. But the pattern is consistent enough across many studies and populations to suggest that diversity in the gut microbial community, the presence of many different species filling many different ecological roles, is in some way protective against the immune dysregulation that underlies allergic disease. Efforts to harness this relationship therapeutically are ongoing. Probiotic supplements, live bacteria given with the aim of supporting microbiome diversity and immune regulation, have been studied extensively in the context of allergy prevention and treatment. Results are mixed and vary considerably depending on which bacterial species are used, what doses are given, at what age, and for how long. The microbiome is vastly complex, and the idea that adding a single bacterial strain in a capsule will reliably produce a particular immune outcome in all individuals is probably too simple. But the field is young, and the research is active, and the understanding of how specific microbial species and their metabolites shape immune function is deepening every year. Mold spores are a particularly interesting class of aeroallergen because, unlike pollen, which has a relatively clear seasonal pattern tied to plant flowering times, mold spores can be present in significant concentrations year-round, both indoors and outdoors. There are hundreds of thousands of known mold species on Earth, and they play essential ecological roles as decomposers, breaking down dead organic material and returning nutrients to the soil. Their spores are almost always present in outdoor air at some concentration. They peak after rain, when decomposing plant material is abundant, and during autumn, when leaves are falling and decaying. Indoors, molds grow wherever moisture is available. Bathrooms, basements, around windows where condensation forms, in walls where water has penetrated, under sinks, around plumbing. The molds most associated with indoor allergy problems include species of Cladosporium, Alternaria, Aspergillus, and Penicillium. The spores of these species are small enough to penetrate deep into the lungs, making mold allergy particularly relevant to asthma. In some studies, sensitization to the mold Alternaria alternata has been identified as a strong independent risk factor for life-threatening asthma attacks. The reasons are not entirely clear, but may relate to the size of the spores, their ability to reach the deepest airways, and certain properties of Alternaria proteins that make them particularly potent triggers of the allergic cascade. Controlling mold exposure indoors requires controlling moisture, ventilating bathrooms, fixing leaks promptly, using dehumidifiers in damp basements. These interventions reduce mold growth at the source, which is a more sustainable approach than trying to filter mold spores from the air after they have already been produced. The spores are small enough to travel long distances on air currents and to penetrate even fairly efficient air filters. Preventing their production is more effective than trying to remove them once they exist. One of the curious facts about mold allergy is that it can produce reactions in some people not just to airborne spores, but to mold in food. Fermented foods, dried fruits, certain cheeses, and even some wines and beers contain mold-derived proteins that can trigger reactions in highly sensitized individuals. Someone severely allergic to Aspergillus species might react to soy sauce, which is fermented using Aspergillus mold, or to cheese produced with mold involvement. This cross-reactivity between inhaled mold allergens and food-associated mold proteins is another example of how the immune system's molecular pattern recognition can create unexpected connections between seemingly unrelated allergic triggers. Animal dander is one of the most pervasive and persistent allergens in modern homes. The word dander refers to tiny flakes of skin shed by animals with fur or feathers. But the actual allergenic component is usually not the skin itself, but proteins secreted onto the skin and into saliva and urine. In cats, the primary allergen is a protein called FeL-D1, produced in the sebaceous glands and the salivary glands. Cats produce it in abundance and spread it across their fur when grooming. It dries, flakes off, and becomes airborne in particles so tiny and lightweight that they can remain suspended in air for hours and penetrate to the finest particles that settle on every surface of a home. Cat allergen is notably sticky. It adheres to surfaces, clothing, and furnishings with a tenacity that makes it extremely difficult to remove. Studies have found detectable levels of cat allergen in homes where no cat has ever lived, presumably transported there on the clothing of people who do own cats. Schools, office buildings, and other public spaces that have no animals in them can have measurable cat allergen levels simply because people who own cats bring it with them wherever they go. For severely cat-allergic individuals, this ubiquity means that truly allergen-free environments are extraordinarily difficult to maintain. There is an ongoing research effort to develop hypoallergenic cats. This has taken several approaches. Some breeders have selected for cats that naturally produce less FeL-D1, and certain breeds, including Siberian and Balinese cats, are sometimes marketed as lower allergen, though the variation between individual animals within any breed is large enough to make broad generalizations unreliable. A more sophisticated approach has involved genetic engineering. One biotechnology company has used gene editing to create cats with a modified FeL-D1 gene, producing animals that secrete far less of the protein. Whether such animals are meaningfully less allergenic for sensitive individuals, and whether they are healthy and behave normally, is still under evaluation. The ambition is significant. The first genetically modified hypoallergenic pet would represent an interesting convergence of cutting-edge genetic technology and one of the most ordinary domestic frustrations known to modern humans. A parallel approach involves not modifying the cat, but modifying the allergen in the environment. There are now cat foods available that deliver IgY antibodies derived from eggs against FeL-D1. Cats fed these foods produce saliva containing the antibodies, which neutralize FeL-D1 as it is produced, reducing the amount released into the environment. Preliminary studies have shown meaningful reductions in airborne FeLD1 levels in homes where cats eat this food. It is a peculiar and creative intervention. Not treating the allergic human, not modifying the cat's genes, but intercepting the allergen in the cat's own mouth before it reaches the human environment. The biology of why some people develop allergies and others do not, even with identical exposures and very similar genetics, remains one of the genuinely open questions in medicine. The answer involves a level of biological complexity that is humbling to contemplate. The immune system is not a single organ or a single cell type. It is a distributed network of cells, tissues, chemical signals, physical barriers, and cellular memories distributed throughout every tissue in the body. The outcome of any particular immune encounter, whether tolerance develops or sensitization develops, whether a response is calibrated or exaggerated, depends on the simultaneous interaction of dozens of variables. The age at first exposure, the dose of the substance encountered, the route of exposure, whether it enters through the gut or the skin or the airways, the concurrent state of the immune system, whether it is currently fighting something else, the composition of the microbiome at that moment, the genetic variants carried in dozens of immune-related genes, the hormonal environment, the stress hormones circulating at the time of exposure. Each of these variables alone can tip the balance. Taken together, they create an almost infinitely branching set of possible outcomes, which is why two children raised in the same house, eating the same food, with the same parents, can end up with completely different allergic profiles. The same system, the same environment, different conversations. This complexity is what makes allergy both fascinating and frustrating to research. There is no single cause, no single switch to flip, no intervention that works reliably for everyone. Progress comes slowly, through large studies, through careful mechanistic work, through the patient accumulation of data that eventually reveals patterns where before there seemed to be only noise. There is something worth sitting with in the relationship between allergies and seasons. The way that the allergic experience, for millions of people, is deeply tied to the rhythms of the natural world. To the first warm days of spring when the trees shake loose their clouds of pollen, to the long grass of June buzzing gold in the afternoon light, to the dry heat of late summer when ragweed sends its inconceivably abundant pollen into air that feels suddenly yellow and heavy. These are the same rhythms that poets have celebrated for centuries, the same turning of the year that connects humans to the landscape they evolved in. For someone with severe seasonal allergies, these seasons can be a source of dread. The beautiful spring morning that other people step outside to enjoy is, for a sensitized nose and pair of eyes, an assault. The meadow that looks peaceful and golden is, at the molecular level, a storm of provocations. And yet, there is something beautiful about this sensitivity too, in the right frame of mind. The allergic person knows the seasons not just by their appearance, but by their immunological fingerprint. They feel the year turning in their own body. Their nose announces the first oak pollen days with a reliability that matches any calendar. They are, in a physiological sense, more deeply entangled with the plant life of their region than those who pass through it unaffected. Every sneeze is, at some level, a conversation between an ancient immune system and an ancient plant. A miscommunication across billions of years of evolutionary history. The plant is simply doing what plants do, reproducing, sending its genetic cargo into the air, trusting the wind. The immune system is simply doing what immune systems do, defending, reacting, treating the unfamiliar with suspicion. Neither is wrong. They simply were not designed with each other in mind. They are strangers in a world they share, having the same misunderstanding every spring, for as long as both have existed. Research into allergy has accelerated dramatically in the 21st century, driven in part by the development of a new class of drugs called biologics. These are not small chemical molecules like antihistamines or corticosteroids. They are large, precisely engineered proteins, usually antibodies, designed to interfere with specific steps in the allergic signaling cascade with a precision that earlier drugs could not approach. The first and most famous allergy biologic is omalizumab, which works by binding to IgE antibodies circulating in the blood, preventing them from attaching to mast cells and basophils. If IgE cannot arm the mast cell cannot be triggered, regardless of what allergen appears. Omalizumab, in a sense, diffuses the weapon before it can be loaded. It has proven effective in severe allergic asthma and in chronic spontaneous urticaria, an allergic skin condition involving recurrent hives, transforming the lives of people who had failed to respond to any conventional treatment. It represents a remarkable therapeutic achievement, the result of understanding the allergy cascade at a molecular level well enough to design a drug that interrupts it at a key strategic point. More recent biologics target other steps in the cascade. Dupilumab blocks the receptor for two cytokines, interleukin-4 and interleukin-1/3, that play central roles in the type 2 immune response underlying atopic diseases. In clinical trials, it has shown dramatic effectiveness for severe eczema, reducing disease severity scores in ways that earlier treatments could not match, and producing changes in skin quality that many patients describe as life-changing. It has subsequently been approved for asthma and nasal polyps and is being studied for food allergy and eosinophilic disorders. It is a drug born from decades of basic science research into the molecular mechanisms of type 2 inflammation, a direct translation from the laboratory bench to the patient's arm. The pipeline of allergy biologics continues to expand. Drugs targeting interleukin-5, a cytokine that drives the proliferation of a class of inflammatory cells called Eosinophils, have proven effective in severe eosinophilic asthma. Drugs targeting the receptor for interleukin-3/3, an early alarm signal released by stressed epithelial cells, are in advanced clinical trials for multiple allergic conditions. The underlying logic of all of these drugs is the same. Map the molecular pathway of the disease. Identify the points where specific signals are essential. Design a molecule that blocks those signals at that point. It is a kind of precision warfare conducted at the scale of individual proteins. The cost of these drugs is currently very high, limiting access for many who could benefit. But the science behind them is advancing quickly, and as the biologics space matures, as biosimilars are developed and manufacturing becomes more efficient, broader access seems a reasonable expectation. The treatment of severe allergic disease is, right now, in the middle of a genuine transformation. Sleep itself has an interesting relationship with the immune system and with allergic disease. The immune system is not uniformly active throughout the day. It follows a circadian rhythm, with certain immune functions ramping up during sleep. Cytokine production changes over the course of the 24-hour cycle. The migration of immune cells to different tissues follows a daily pattern. There is even evidence that the formation of immunological memory, the process by which the immune system consolidates its learning from recent encounters, is enhanced during sleep in ways that parallel how the brain consolidates memories of experiences and learning. For people with allergic diseases, sleep is often disrupted. Nasal congestion worsens when lying flat because the redistribution of blood flow in the supine position increases blood volume in the nasal vasculature, which is already prone to congestion in allergic rhinitis. Nighttime exposure to dust mite allergen in bedding is highest during the hours of sleep. Asthma symptoms follow a circadian pattern and are often worse in the early morning hours, between about 2 and 4 in the morning, when airway resistance is at its physiological peak and when the anti-inflammatory effect of endogenous cortisol is at its nadir. The resulting poor sleep has consequences that ripple outward through health and well-being. Poor sleep impairs cognitive function, worsens mood, disrupts appetite regulation, reduces immune effectiveness, and increases the perception of pain. Children with poorly controlled allergic rhinitis or asthma frequently have disrupted sleep, which affects their concentration, their school performance, their emotional regulation. The allergic disease is not just a physical inconvenience. It reaches into every domain of the person's daily life through the pathway of sleep, which is one of the reasons that effective treatment of allergic disease matters so much, not just for the relief of sneezing or the reduction of wheeze, but for the restoration of ordinary, healthy, restorative sleep. And with sleep, the restoration of everything that sleep makes possible. The skin microbiome, the community of bacteria and fungi living on the surface of the skin, turns out to play a role in allergic skin disease that mirrors the role of the gut microbiome in food allergy and asthma. Healthy skin is colonized by a diverse community of microorganisms. These organisms are not simply tolerated. They actively contribute to the skin's barrier function, to its immune tone, to its ability to distinguish harmless environmental contact from genuine threat. The most intensively studied skin organism in the context of eczema is Staphylococcus aureus, a bacterium that colonizes the skin of nearly all eczema patients in significantly higher numbers than on the skin of people without eczema. Staphylococcus aureus is a complex organism. Most of the time, on most skin surfaces, it is a relatively harmless commensal. But in the environment of eczematous skin, where the barrier is disrupted and the immune tone is already inflamed, it takes advantage. It produces toxins that function as superantigens, massively amplifying immune activation. It damages the skin barrier further. It provokes further inflammation, which disrupts the barrier more, which allows more bacterial colonization, in a cycle that drives the disease forward. Reducing Staph aureus burden on the skin is one of the key goals of eczema management. and many of the topical treatments used for eczema work in part by reducing the environment that Staph aureus thrives in. The contrast between Staph aureus and another skin bacterium, Staphylococcus epidermidis, which is almost universal on human skin and strongly associated with skin health, illustrates the nuance of the skin microbiome perfectly. Both are staphylococci. Both live on skin. But one drives inflammation and disrupts the barrier, while the other appears to actively protect it and to train the immune system toward tolerance of harmless environmental substances. The differences between them lie in their proteins, their metabolites, the signals they send to the immune cells in the skin. They are the same in broad strokes and entirely different in the ways that matter. The science of the nose itself deserves a moment of quiet attention. The olfactory epithelium, the small patch of specialized tissue high in the nasal cavity responsible for the sense of smell, contains roughly 6 million olfactory receptor neurons. Each of these neurons extends a thin, hair-like projection into the mucus layer coating the nasal surface. And these projections contain the receptor proteins that bind odorant molecules. When you walk into a kitchen where something is baking, or step outside after rain, or catch a familiar scent that suddenly pulls a memory forward with startling vividness, it is these neurons firing, sending signals directly up through tiny holes in the skull into the olfactory bulb in the brain, and from there into the limbic system, the seat of emotion and memory. This direct anatomical pathway from the nose to the emotional and memory centers of the brain is unique among the senses. Unlike vision or hearing, which route through the thalamus before reaching the cortex, olfactory signals reach the amygdala and hippocampus with remarkable directness. It is why smell is so powerfully evocative of memory and emotion, why a certain scent can transport you back to a specific moment with a vividness that simply hearing a description of that moment cannot produce. The olfactory system is ancient, shared with fish and reptiles and every vertebrate that has ever lived, and it connects to parts of the brain that predate conscious thought itself. When allergic rhinitis inflames and congests the nasal passages, this ancient pathway is muffled. The odorant molecules cannot reach the olfactory epithelium efficiently. The neurons cannot fire. The world loses its smell, and with it, something more than just a sensory experience is lost. People who live with chronic anosmia, the absence of smell, often describe a flattening of emotional experience that goes beyond the inconvenience of not tasting food fully. Smell is woven into how we read spaces, into appetite and satiety, into the subtle social cues of proximity and safety. Losing it changes how the world feels in ways that are difficult to articulate and easy to underestimate. Restoring smell, by effectively treating the allergic rhinitis underneath, is therefore not a cosmetic goal. It is a restoration of a sense that connects the person to the emotional and memorial texture of their life. And for many people with well-controlled allergy, the moment when smell returns, when the first cup of morning coffee is suddenly full and real and complex rather than flat and approximate, is described as one of the most pleasant rewards of finally getting treatment right. Nasal polyps deserve a mention in the allergy story, because they sit at the intersection of allergic and non-allergic inflammation in a way that illuminates both. Nasal polyps are soft, non-cancerous growths that develop in the lining of the nasal passages and sinuses, typically in the areas of the sinuses that drain through the nasal cavity. They develop in the context of chronic inflammation, and they are strongly associated with eosinophilic inflammation in particular. People with asthma are more likely to develop nasal polyps. People with the aspirin sensitivity syndrome, the non-immunological hypersensitivity to aspirin and other non-steroidal anti-inflammatory drugs, have an especially high rate of nasal polyp development in a condition sometimes called Samter's triad. Nasal polyps obstruct the nasal passages mechanically. When they are large, they can completely block airflow through the nose, eliminate the sense of smell, cause chronic sinusitis, and impair sleep quality profoundly. They are treated with topical nasal steroids, which can reduce their size, and with surgery when they are too large or too numerous for medication to manage. But they recur. Surgery can remove the polyps, but unless the underlying eosinophilic inflammation is controlled, new polyps grow back, and the surgery must eventually be repeated. Dupilumab, the biologic that targets the interleukin-4 and interleukin-1/3 pathways, has proven highly effective at reducing nasal polyp size and eliminating the need for repeated surgeries in many patients. It is another application of the same biological insight applied in a slightly different clinical context, reducing the eosinophilic inflammation that drives the polyps through the same pathway that drives eczema and asthma. The interconnectedness of these conditions, asthma, nasal polyps, eczema, food allergy, allergic rhinitis, all sharing underlying mechanisms, all part of the same spectrum of type 2 immune dysfunction, is something that took medicine decades to fully appreciate. For most of the 20th century, these were treated as separate diseases, managed by different specialists, approached with different drugs, thought of as essentially unrelated except for a vague family resemblance. The molecular revolution in immunology has made clear that they are not separate at all. They are expressions of the same underlying immune dysregulation in different tissues. A person with eczema and asthma and nasal polyps does not have three separate diseases. They have one disease expressed in three places, and a drug that targets the shared molecular mechanism can improve all three at once. This unified view of allergic disease is one of the most intellectually satisfying developments in modern medicine. It does not simplify the clinical complexity, which remains real and demanding, but it gives clinicians and patients a coherent framework for understanding why these conditions tend to cluster together, why treating one often improves others, and why the same biological logic underlies what previously seemed like unrelated problems. The future of allergy treatment is likely to involve personalization in a way that current medicine has only begun to approach. Allergic diseases are not monolithic. Two people who both carry a diagnosis of allergic asthma may have meaningfully different underlying biology. One might be driven primarily by eosinophilic inflammation, responding to allergen exposure. Another might have a neutrophilic pattern, driven by infections or pollutants. One might respond dramatically to inhaled corticosteroids, while another does not. One might benefit from a biologic targeting interleukin-5, while another needs one targeting the IgE pathway. The phenotypes, the observable features of the disease, overlap, but the endotypes, the underlying molecular mechanisms, can be quite distinct. Advances in molecular diagnostics are beginning to make it possible to characterize a person's allergic disease at this deeper level, to measure the specific cytokines circulating, to profile the gene expression in airway cells, to assess microbiome composition, to map the specific IgE sensitization pattern in detail. This kind of comprehensive characterization, sometimes called precision medicine or endotyping, should, in theory, make it possible to match each person to the treatment most likely to work for their particular variant of the disease, rather than following a generic stepwise escalation of increasingly powerful drugs until something sticks. The practical implementation of precision medicine in allergy is still years or decades away from being routine. The diagnostics are complex and expensive. The treatment algorithms to translate molecular profiles into treatment choices are still being developed, but the direction is clear. The future of allergy care is less one-size-fits-all and more a tailored, biology-driven conversation between what the immune system is doing and what medicine can offer to guide it toward balance. There is, threaded through all of this science, a kind of quiet wonder. The immune system that misidentifies a pollen grain is the same system that identified and remembered every significant pathogen you have ever encountered. The mast cell that fires histamine at a harmless food protein is the same mast cell that, in a different context, helps repair tissue and defend against real invasion. The IgE antibody class that powers anaphylaxis is the same antibody class that spent millions of years protecting your ancestors from worms and parasites that have not troubled most humans for generations. Every allergy is, in some sense, the price paid for a system so sensitive, so loyal, so relentlessly devoted to the business of protection that it cannot always distinguish between a genuine threat and a benign stranger. It is not a flaw in design. It is the cost of a design so committed to its purpose that it sometimes overshoots. A system that never made mistakes would be a system too cautious to do its job. The immune system makes this particular kind of mistake because it is so deeply committed to its primary task, which is keeping you alive, that it will err on the side of aggression rather than complacency. And then there is the vastness of what it gets right. Every day, without any instruction from your conscious mind, the immune system correctly identifies and tolerates the thousands of harmless substances that pass through and over your body. The food proteins in your lunch, the bacteria in your gut that you cannot live without, your own cells, which it must distinguish from invaders moment to moment. The skin bacteria that protect as much as they might one day threaten. All of it managed. All of it navigated. All of it the quiet work of a system that does not ask for attention and does not announce itself. The allergic reaction, the sneeze, the itch, the watery eye, is the part that gets noticed precisely because it goes wrong. The enormous, continuous, invisible correctness that surrounds it is the part we forget because it simply keeps happening under the surface, below the level of awareness, every second of the whole long arc of a life. And so we have reached the end of our quiet journey. There is one last thing worth holding before we close. Allergy research is one of the areas of medicine where the gap between what is known and what is not known remains most honestly, most productively open. Researchers who work in this field tend to speak with a particular kind of intellectual humility. The immune system is so complex, the interactions so numerous, the individual variations so large, that confident pronouncements about any single cause or any single cure tend to unravel quickly when tested against the full diversity of human experience and human biology. The history of allergy medicine is punctuated by ideas that seemed perfectly logical and proved, on careful testing, to be wrong. Avoid allergens in infancy to prevent sensitization. Wrong in key cases. Hygiene explains the modern allergy epidemic. True in some directions, incomplete in others. A single drug will work for all asthma, repeatedly and humblingly disproven. The scientists who persist in this field do so in the presence of genuine uncertainty. They hold their hypotheses carefully, test them rigorously, and revise them honestly when the evidence points another way. This is science working as it should, not as a series of triumphant discoveries, but as a slow, patient, collaborative narrowing of what is unknown. Each generation of researchers inherits a smaller but still vast territory of the not yet understood. Each generation maps a little more of it, hands the map to the next, and leaves space for the discoveries no one has yet imagined. For the people who live with allergic disease, this ongoing research is not abstract. Every clinical trial testing a new biologic represents the possibility of life changed. Every study examining early introduction of foods represents children who will not grow up carrying epinephrine. Every investigation into the microbiome is a step toward understanding what creates vulnerability and what protects against it. The science is slow by the standards of human impatience. By the standards of how hard the questions are, it is moving with remarkable speed. There is something comforting in knowing that the condition responsible for so much human misery, from the mildest case of spring sniffling to the most severe, life-altering disease, is one of the most intensively studied areas of biology in the world. Thousands of laboratories, hundreds of thousands of patients enrolled in trials, decades of accumulated knowledge building toward treatments that would have seemed like science fiction to a hay fever sufferer in the early 20th century. Not cures, not yet, but better management, better prevention, and for an increasing number of people, genuine disease modification through immunotherapy that lasts for years after treatment ends. The immune system that causes all of this is the same one keeping you alive right now, distinguishing self from other, remembering threats and responding to them faster the second time, learning tolerance for the things that should be tolerated, making, occasionally, the wrong call, then sometimes being patiently, carefully retrained. There is nothing in the human body quite like it. Nothing so distributed, so adaptive, so ancient, and so intimately tied to how each person experiences the world they move through. It is yours, running quietly beneath everything. Tonight, as you sleep, through the science of allergies. We have traveled from the outermost surface of a pollen grain to the deepest chambers of immunological memory. We have visited the inside of a mast cell in the moment before it fires. We have walked the branching passages of a lung and the vast, folded surface of a gut. We have met the dust mite in its mattress paradise, the mold spore drifting on an autumn breeze, the cat allergen clinging to a coat long after the cat has gone home. We have followed the signal of histamine from the receptor to the nerve to the sneeze. We have seen the immune system at its most loyal and at its most confused. We have watched it learn, watched it remember, watched it sometimes, slowly, be taught to let go of fears it did not need to carry. There is so much still to understand. The full picture of why allergies develop, why they seem to be increasing in modern life, how the microbiome and the skin and the gut and the brain all contribute to the balance between tolerance and reaction, why some people outgrow allergies and others carry them for a lifetime, what the ideal early environment looks like to give an immune system the best chance of settling into peaceful coexistence with the world. These questions are being asked right now by thousands of scientists in laboratories and clinics and population studies across the world. The answers are arriving slowly, the way scientific answers always do. Through careful observation and honest disagreement and the patient accumulation of evidence. But tonight you do not need any of the answers. Tonight, all you need to know is that the tiny, quiet machinery inside you is doing its work. Somewhere in your bloodstream, a T cell is reading a molecular signal. Somewhere in your gut, a bacterium is producing a short-chain fatty acid that will reach an immune cell and whisper something calming. Somewhere in your skin, a mast cell is sitting quietly, loaded and at rest, finding nothing in the air that needs a response. The invisible city is running. The invisible city is always running. And you are here, breathing slowly. The breath coming in, warming as it crosses the intricate surface of your nasal passages, filtered and humidified before it reaches the branching darkness of your lungs. The exhalation soft and even. The body doing what bodies do, without effort, without thought, without asking anything of you at all. You are, in this moment, being taken care of by systems so ancient and so finely tuned that to comprehend them fully would take more than a single lifetime. So, you do not need to comprehend them tonight. Just let them work. Just let the breath move. Just let the slow, tireless, invisible work of being a living thing continue on its own, as it has always done, as it will do through every hour of your sleep. If you are still awake, the next video will be waiting for you when you are ready. But if your eyes are heavy, if the world outside this quiet moment has grown soft and far away, let it go. Let the breath slow. Let the thoughts drift apart like seeds on a spring wind, light and purposeless, carried somewhere soft. The body knows how to rest. It has always known. Let it. Good night.